Okay, so I think that it's time to start. Hello, everyone. Welcome back for the third talk of this half-day dedicated on interpretability via random forest of the ENBIS workshop on interpretability for Industry 4.0. That is just before the round table in half an hour. So our next speaker is Clément Bénard, and his talk is about black box explainability and variable importance in random forest. It is quite different from the one which is on the slide, but it's perfect. Clément Bénard is he graduated from Cornell University and École Centrale Paris in 2014. And he's since 2015 research engineer in machine learning and statistics at Safran Tech near Paris. He is currently also a PhD student co-supervised by Erwan Scornet, Gérard Biot, and Sébastien Davega at Sorbonne University about interpretability with random forest. So welcome, Clément, the floor is yours.
So hello, so for the last part of the pillar, I'm going to talk about postdoc methods for interpretability, and especially Sobol indices and Shapley effects for random forest. So the main way to interpret random forest may be the MDA, which is a built-in variable importance algorithm specific for random forest, and which is widely used at least in the past 2 decades. So the main point of the MDA is that it's extremely fast to compute an importance measure once you have a random forest. However, the MDA has several flaws. So in particular, there is no understanding of what the MDA is really estimating. And secondly, there are several empirical studies showing that the MDA is biased when inputs are dependent. So our objective here is first to derive a theoretical analysis of the MDA to understand why the MDA is biased when inputs are dependent, and to draw connections with Sobol indices that Sébastien introduced in the previous part. And secondly, our second objective is to introduce the Sobol MDA algorithm, which fixes the flaws of the original MDA. So first, let me introduce a very standard setting with an input vector X of dimension P, an output Y, which is real valued, and a dataset Dn made of n IID observations. So to introduce the MDA, I need to recap quickly how the random forest works. So a random forest aggregates a large number of random trees. So as you can see on the right, a tree partitions the input space with splits of the shape x2 less or greater than 1.2, for example. And the main feature of the forest is that each tree is randomized through a variable theta. So theta has 2 components to randomize the tree. The first component, theta s, is used to resample, to bootstrap the data prior to the construction of the tree. And the second component is theta v, which is used to randomize optimization at each node. So each node, the tree looks for the best variable and the best floor to partition the data in 2 children nodes so that the variance of the output is reduced. And we do not optimize over all the input variables, but only across a random subset of the input variables. So M is the number of trees, and we denote by M, and X theta M, the forest estimates at the query point X. So now we can dive into the theoretical analysis of the MDA. So the principle of the MDA it's to compute the decrease of accuracy of the forest when a given variable is noised up. So more precisely, we first fit a random forest with the data, we compute the accuracy of the forest, and in the third step, we copy the data and we randomly permute the values of a given input variable xj. And the goal is to break the dependence between xj and the output y. And finally, compute the prediction for this new data, new permitted data, and get the decrease of accuracy with respect to the original accuracy when the data is not permitted. And this gives the decrease of accuracy is definition of the MDA. And of course, if this decrease is 0, it means that the variable has no influence in the prediction process of the forest. And if this decrease of accuracy is high, it means that the variable strongly influence the prediction mechanism of the forest. So let's take a toy example with a data set of size 5 data points. Let's say we want to compute the MDA for variable xj in green. So we copy the data, we permute the values in green to get the column in orange with the permuted values. Then we compute the prediction of the forest for both data sets. And with the two sets of prediction, we compute the output x-plane variance. For example, on the left, we get 16.4, and on the right, we get 13.7. And then we subtract the two, and this defines the MDA for variable xj. So in this procedure, I did two things with the data. First, I feed the forest, and secondly, I have computed the accuracy. And it is a good thing to do these two operations with the same data. And of course, the answer is no, because when you do that, you overfit and you will get an inflated accuracy. So the question is how to handle this in practice. And actually, when we look at the literature and the implemented algorithms, we see that there are several ways to tackle these problems. So the first way is what we call the train test MDA. So it uses a very basic trick to split the training data in two parts. The first part to train the forest, and the second part to estimate the accuracy. And this is not used a lot in practice because we don't like to do that too much, to break data in two parts. Instead, there is a trick called the out-of-bag sample. So the idea is that when we build the forest, the data is bootstrapped here to the construction of each tree, which leaves aside a portion of the data for each tree, and we can use this out-of-bag sample as a test set to compute the accuracy. So if we go back to our toy example at the bottom of the slide, let's say that when we bootstrap, we select only the 3 points in blue, then the out-of-bag sample is obviously the 2 points in red. So overall, there are mainly three versions, three definitions of the MDA. The train test MDA, and you also have the Bryman-Cutler MDA and the Ishoren-Kogalur MDA, which both use this out-of-bag sample to perform the estimation, and the only difference is the way they compute the error. So we're going to derive a asymptotic analysis of the three algorithms, and we'll see that they do not converge towards the same quantity, which means that there are in fact different importance measures. So to begin, we're going to focus on the Bryman-Cutler, which is the original definition from Bryman and the most widely used. So we need a few notations. So first, the out-of-bag sample is, in our example, it's the index is 2, 5. Next, n of NL is the size of the out-of-bag sample, which is 2 in our example. And finally, we use xi pi jl, the observation I, where the component j has been permuted across another out-of-bag observation for tree L. Okay, so in our example, for example, for observation 5, for the component j, we permute it with the second observation to get xi of pi jl. So now we can give the exact formulation of the Bryman MDA, which is given by this sophisticated formula. So let's break it down slowly. So in green, we have the quadratic risk of tree L. In orange, we have the inflated risk for tree L, where the component J is permuted, is noised up. So we subtract the two risks that are computed over the full out-of-bag sample for each tree through the blue sum. And finally, we average this over all trees. So it's interesting to notice that we're not really computing the decrease of accuracy of the forest, but we're rather doing a Monte Carlo estimation of the tree decrease of accuracy. So now that we have defined the MDA, we can move forward toward the convergence analysis. To do so, we need several assumptions. So first, the output Y is defined at the following regression model, M of X plus an independent sub-Gaussian noise. The input X belongs to the unit cube and admits a density bounded above and below with positive constants. The assumption is not very restrictive. We see that it's quite general. It allows inputs to be strongly dependent, for example. We need a second assumption, which is more technical. The theoretical tree is consistent. So in general, it's only always true for additive models. In the general case, it is not always true with Bryman forest, but with very small modification of the forest algorithm, this assumption always holds. So it's quite mild. I'm going to skip the formal definition to go to the third assumption, which is that the tree partition is not too complex with respect to the sample size. So we do not grow tree, we do not use fully grown tree. We control the complexity of the final partition. And again, I skip the formal formulation. So under the three assumptions, we have that the Bryman MDA converges towards the theoretical quantity, the expectation of the square difference between M of X minus M of X pi J, where X pi J is X with the component J replaced by an independent copy. So it's not very surprising to have these asymptotic limits. And what we can notice is that it's hard to interpret the meaning of the theoretical counterpart. So we're going to use several indices to break down these limits. So let me recall very quickly what Sébastien said. So let's say when dimension 2 with x1 and x2, and the black box is the variance of the output y. So we can break it down with the variance generated by the noise epsilon and the variance generated by x1 and x2. In blue, it's a total stable index, which is a proportion of output variance, which is lost when we remove x1 from the model. And the brown circle is the full total stable index, which is the blue part, and in addition, the contribution to the output variance generated by interaction and dependence between x1 and x2. So using this, we can now break down the MDA limits as a sum of the unnormalized total stable index plus the full total stable index plus a third component in red, MDA3, which is not a non-importance measure and is in fact not very relevant. The issue with this term is that a very influential variable can have a null MDA3. So in fact, this term is a bias in the MDA limits. And for example, it can have a very high value when there is a combination of strong dependence and strong interactions. So if you conduct the same asymptotic analysis with all MDA versions, the train test MDA and the IK MDA, we also have the same decompositions, and we can notice two things. So first, in all limits, we see that we have MDA3, we have the same bias. And secondly, the IK MDA does not have the same limit of the first two versions. which means that in fact, these measures are different importance measures. If we add more restrictive assumptions on the input distribution, we can recover more meaningful counterpart for the MDA. So for example, if the input components of X are independent, then we recover the total subtle index, which is quite meaningful because it gives you the proportion of output variance lost when the variable xj is removed from the model. So it's usually what one is looking for by computing the MDA. Instead, if we assume that the regression function is additive, we also get rid of the noisy component MDA3 and recover meaningful quantities, but which are different than in the independent case. So to sum up, we can say that when the inputs X are dependent and have interactions, the MDA has a noisy term MDA3, and the MDA therefore misleading. Secondly, in the various MDA implementations, the algorithms are not equivalent because they have different asymptotic limits. So we should be careful when using the random forest packages. When we're doing variable selection, the most relevant components is the total subtle index, as it gives you a proportion of output variance lost by removing a variable. And this is why we have developed the subtle MDA, which is a fast and consistent estimate of these blue components of total subtle index for random forests. So let's move forward and present the subtle MDA. So the main principle is to forget about this idea of permuting the data and to use projection instead. So let's give an example. So first, the formula of the subtle MDA is again the subtraction of two risks. The inflated risk minus the original risk of the forest. So we take this small example in dimension 2. So we have x1 and x2. And here in green, it is the risk of the original forest, of the Brahman forest. So on the figure, we have the partition of a single tree. And to predict, to get the prediction for point X, we're going simply to average the green points that fall in the same cell as X. Now, let's say we want to compute the MDA for X2. So we want to get rid of X2 in the prediction process. So instead of permuting, we're going to project the partition along X2. So here it's going to be on the subspace generated by X1. And instead of the blue partition, we recover the red partition. And now to predict X, we're going to average the green points on the red line. And this enables us to get the risk, the inflated risk, when we remove X2 from the prediction process and to get the subtle MDA estimate. So an important property of the subtle MDA is that it is in fact a consistent estimate of the total subtle index. So we see that now we recover the appropriate theoretical counterpart. So a small experiment to illustrate the subtle MDA. So let's say we have 200 input variables divided in 5 groups. Each group is independent of the others and made of 40 variables that are strongly correlated. The regression function is defined as the sum of one variable from each group with the higher weights for variable 1. So we fit the forest, we compute the subtle MDA, BCMDA, and the IKMDA. And in blue, we have the 5 relevant variables involved in the regression function. And we see that only the subtle MDA is able to rank the relevant variables at the top 5. For the BCMDA and the IKMDA, Because of the correlation, variables from the first group are going to be top rank, even if they are not involved in a regression function. So we made additional simulation in our paper, if you're interested, with an analytical example, and also we illustrate the points of the subtle MDA to the backward variable selection with real data. An interesting extension is also the case when the random forest is not efficient. So we can always use another black box model, which is efficient on the data. Use this new model F hat to generate a very large sample, and then feed the forest and run the subtle MDA on top of this new sample. So it's a little trick to benefit from the subtle MDA, even when the forest does not perform very well on the data. Okay, so finally, we can extend the principle of the subtle MDA to Shapley effects. So let me introduce what are Shapley effects. So it's another importance measure, and they were originally defined in economics and game theory a long time ago. And the purpose of Shapley effects is to attribute the value produced by a joint team to its individual members. And of course, the value produced by the joint team is going to be much higher than the simple sum of the contribution of each individual working alone, because they're working as a team. And so we want to reattribute, to reallocate the full contribution of the team to each member. So the idea of Shapley effects is to measure the difference of produced value between a subset of the team and the same sub-team plus an additional member. And we average this over all possible sub-teams for a fixed member. And it defines the Shapley value for the specific member. And we can do that for all members. So recently, Owen adapted this to machine learning, where a member of the team is now an input variable, and the value function is the explained output variance. So formally, the Shapley effect of variable xj looks like this. So it's going to be a sum over all possible subteams U. And we see that the ratio on the right is going to give the additional explained variance when we add variable j to the team U. And the term in front of the ratio is simply to compute the average over all possible subteams that are not including variable xj. So the nice property with this importance measure is that it equitably allocates contributions due to dependence and interactions across all input variables. And if we sum the Shapley effects for all variables, it gives 1. So it really breaks down nicely the output explained variance across all input variables. So there are 2 obstacles to estimate Shapley effects in practice. First, the computational complexity is exponential with the dimension p, because we're doing the sum over all possible subsets of variables. And secondly, we need to estimate the variance of the conditional expectations for any subset U, which is quite difficult and computationally costly. So in the literature, the first point is addressed using Monte Carlo methods. So instead of a brute force approach where we compute the variance of the conditional expectation for all subset U, we randomly sample only a few hundred sets U, which is computationally much faster and gives quite good results. And secondly, for the second point, what is done usually is to use strong approximation of the conditional distributions. Typically, the joint distribution is approximated as the product of the marginals, which is of course a very strong approximation. So we introduced SHAF for Shapley effects for random forest. And the goal is to improve Shapley effect estimation using random forest. So for the Monte Carlo method, we're going to use importance sampling to not sample completely randomly the subset U, but to focus on the most relevant variable subsets U, which involve interacting and influential variables. To do this, we're going to do something very similar to Cirrus. We're going to estimate the occurrence frequency of each variable subset U in the forest, denoted by p hats. And then we're going to sample the subset U using these weights, p hats, as a discrete distribution. So we see that it's going to bias the samplings towards variable subsets that are very influential and have interaction terms. Secondly, to estimate the variance of the conditional expectation of Y conditional on XU, we're going to generalize the principle of the projected forest algorithm by simply projecting the tree partitions on the subspace generated by the variables in U. And we denote the estimates by V hats. And finally, there is a trick to recover Shapley effects by solving a weighted linear regression as defined on the slide. So I'm going to skip details, but when you minimize this cost function in beta, actually you exactly recover Shapley effects. Okay, and the nice property of our SHAF algorithm is that with an additional assumption 4, which say that the number of subsampling sets Kn and the number of trees Mn grows to infinity, under that we have the consistency of SHAF toward theoretical Shapley effects. Provided that we have enough data, we're going to be arbitrarily close to the true value, to the true Shapley effects. So to conclude, we can say that there are strong connections between the MDA in random forest and Sobol indices, and that the theoretical analysis show that the MDA does not target the appropriate quantity when input variables are dependent. This is why we developed the Sobol MDA based on projection of the tree partitions to fix the flows of Breiman MDA. And there is a package available online if you're interested. And next, we generalized the Sobol MDA to SHAF to estimate Shapley effects with random forest. And again, there is a package online available if you're interested. So I'm done. So maybe we can switch to questions if there are any.
Thank you, Clément, for this excellent talk and very informative. I will dive into the numerous questions, and we have 1 minute, so we can take 5 minutes more if you agree, and also if Bertrand agree with that. The first question is from the Naples. It is from Pier Cesare Secchi. So Pier Cesare, if you want.
Very quick, but it's a small detail that I missed. And so if you can go back to your slide 27, where you were showing your first asymptotic result. So my question is, what I missed is, are you averaging, are you taking the expectation also with respect to the permutation, or you, given the permutation, you take the expectation? That's something I missed also in the results that come later on. So when you are evaluating the MDA, are you evaluating by averaging over all possible permutation of the variable that you are looking at?
Yes, actually, maybe we can see that on the formula here. Actually, you see you're averaging over all possible trees of the forest, the M trees, and actually you're doing a permutation of the out-of-back sample for each tree L. Okay, so next in the assumption, you have that the number of trees.
Unfortunately, we cannot see your slides, but so
I cannot see the slide.
no, but you are averaging with respect to all the possible. I mean, you are averaging with respect to the random permutation that you are doing.
Yes, when you take the expectation,
okay,
it's done over theta.
so it's not conditional on the
permutation.
Okay.
Thank you. Perhaps Bertrand, if you want to ask directly your question, or prefer.
Yes, thank you, but maybe you ask better than me, but I can ask my question. It's just the question that in slide 40, you say that the algorithm to compute Sobol MDA is to generate a large sample from F hat. Okay, but I wonder if you have fit F hat on a small size data set and you don't know the underlying input distributions, what kind of idea we can use to generate a large sample of inputs in order to generate a large sample of predictions?
Okay, so a typical setting where the random forest works well is when you have quite a lot of data and the data is sparse. So it happens, especially in numerical simulation, that you have a setting with a small sample, function is quite smooth and you have no noise. So in this particular setting, kriging is going to perform much better than random forests. So typically you can fit a kriging model, which is going to completely outperform the random forest, and then do a very big Monte Carlo simulation to generate samples in the input space and get the predictions with the kriging model, which build your new dataset D prime. And then you can run the forest on top of this large sample and run the Sobol MDA. Does it answer your question?
Not totally, because in fact, I had two questions in one.
Okay.
When you don't know your underlying input distributions, how can you generate new data?
Okay, you're saying that to be able to do that, you need to know the joint distribution.
Yes, and if you don't know,
you need to estimate the joint distribution to do that.
so you need to do that.
Yes, I think you're correct. You may need to do that first. Yes. Yes, I think you're correct.
Okay, thank you.
Thank you. A very last question from Ulrike Grandpige. I'm always puzzled by the use of the term bias for variable importance metrics. The example used in the talk, groups of 40 correlated features each, was again of a nature that does not convince me that the unbiased Sobol MDA is necessarily better. Correlation in real life, where we haven't gone in with a known model, stands for an uncertainty in the causality chain, which may, and for some proposers should, be reflected in the importances.
So I think this is a very good question. The relevance of the importance measure completely depends on the final objective we're looking for. And here, the Sobol MDA is going to be the right definition of importance measure in the case where you're trying to do backward variable selection, because at each step you want to detect the variable you can remove with losing the minimum information. And this is what the total Sobol index tells you. Now it's true that if you have different final objective, which can of course be the case when one is doing a variable importance analysis, other importance measures may be defined differently. The point is that in the BC MDA and IK MDA, the MDA 3 is meaningless, so that there is absolutely no clear interpretation of what it means. So the BC MDA and IK MDA are going to be irrelevant to any final objectives. But of course, the sub-all MDA can also be irrelevant for other objectives. For example, for other types of goals, Shapley effects could be better.
Okay, thank you very much. I have to stop now. Thank you again, Clément, and also Erwan and Sébastien for their talks. And I just want to now hand over the roundtable to Bertrand. Bertrand, yours. The floor is yours.
Thank you very much. Hello, everybody. Do you hear me correctly? Yes?
Yes.
Okay, thank you. So, sorry. Okay. Or maybe I prefer to put it like this. So I propose to discuss a few topics close to the talks of this morning on this roundtable. So the main theme of the roundtable and of this morning is the connection between machine learning, rule-based systems, and sensitivity analysis. So we had 3 talks very close to these topics, and these talks have introduced all the necessary things to discuss. And so thank you very much, Erwan, Sébastien, and Clément. And so I have prepared this roundtable with contribution from few people, from Gérard Biot, Nicolas Bousquet, Jean-Michel, Erwan, and Vincent Touvenot. Okay, so I propose to show you first the 4 topics that we have proposed. Okay, and after I will give the talk to people who can discuss this topic, and we will take some questions from the audience, of some comments of the audience directly, and so do not hesitate to say something in the chat or to raise your hand. Okay, so the 4 topics are the following. So first, we can discuss the sparsity hypothesis induced by random forest-based methods and the implications of this sparsity hypothesis. Second, we can discuss about the close cooperation that can be built between the machine learning and what we call numerical artificial intelligence algorithm, but it means machine learning, and symbolic artificial intelligence systems, which are in fact for us the rule-based systems in this context. Third, I would like to underline the need to clarifying the goal of the explainability issues in the machine learning-based industrial process. Maybe many of participants can say something on this topic. And last, as you have seen this morning on the several talks, you can see that we can develop a close connection between the machine learning interpretability issues and what has been done in the sensitivity analysis of model outputs that I well know, and Sébastien also well known. Many other people here can discuss about this very close connection that we can do. Okay. So first, about the sparsity hypothesis induced by random forest-based methods. This is an issue that has been shared by Nicolas Bousquet. So maybe, excuse me, I have to do something. Maybe we can give the talk to Nicolas. Okay, I can do this myself, but I have some difficulties. Maybe Jean-Michel.
Nicolas, you have the floor now.
Yes. So Nicolas, if you agree, you can present yourself, and after you can explain to the audience all the ideas that you have explained to me.
Thank you very much, Bertrand. So, hello everyone. I am Nicolas Bousquet. I am a research engineer at EDF. Just a small word to begin. I was really impressed by all the talks of this morning. I know a little bit of Cirrus, but the recent development made by Clément about Chaplet were really interesting. So thank you for all the speakers. Yes. So my question is probably very basic, in fact, and maybe naive. As an engineer specialized in risk assessment, when I focus on what I want to interpret something, usually I want to interpret an issue. Usually when we work on critical systems, like industrial ones, of course, in the meantime, usually we don't want to discuss so much about the behavior of this model. You know, it works, etc. But when we place something into production, as we say, we need to audit this kind of model, of machine learning based models, for instance, or hybrid models based on numerical models on machine learning models. And usually we want to justify the use in critical situations. And for me, the usual hypothesis of sparsity, for instance, if you were looking for extreme cases, extreme situations, usually we make some hypotheses like this. And I try, if I remember well, that when we use trees on rodent forests, sometimes this hypothesis is key for building the model. And I think for Cirrus, it was explained this morning, but I remember that because we want to have a small number of branches in the trees, so this hypothesis seems very key to this. And for me, it can be difficult to justify this, because in this case, what we want to predict, to explain, is quite difficult and probably undergoes very large number of variables. So I would like to know if it could be possible first to show that the validity of this hypothesis, if it is really key for the development, and if we can do something, extend the framework that we have discussed this morning.
Okay, thank you. Thank you for this. So I propose to give the talk to Erwan or Gérard, if you want to say your comments about these issues.
Maybe I can start. Can you hear me?
Yeah.
Yes.
Yeah.
Okay. So first of all, so maybe I can start and leave the floor to Sébastien and Clément, because it was not so clear in my email, but the answer here was prepared with Clément and Sébastien. So basically, first, maybe a first question is like the sparsity we want to have in the data, as you mentioned. So in many data set and in many applications, when we want to find interpretability, usually we assume that the data are sparse, so the signal is the output is related to a small number of input variables, and I think we cannot remove this assumption, because otherwise, for example, if you consider a model which is an additive model where all input variables are relevant for making the prediction, then at the end you cannot have an interpretable model, because if you want to grasp all the relation between the input and the output, it would require to put all variables, all input variables as important variables. So usually we assume this sparsity result just to be able to say that in the end we can build an interpret model Otherwise, I think it would be too complicated. Besides, if we consider maybe more generally, if we consider an additive model which is not sparse, random forests are going to perform very badly on this model, because we know that they are not the best suited algorithm for linear relation between output and the input. But your question was also related to the depth of the tree and the order of the interaction we want to look at. It is again a bit the same answer, is that it may be, and I think Sébastien talked about that also, it may be too complicated for the practitioners if we say at the end that the interaction we want to look at is an interaction of order 6 or 7. Whereas if we say that the interaction is of order 2, maybe we're going to lose a little bit the signal, but in the end we can make some action based on that. So it's again a compromise between what we are going to be able to do, the decision we want to make, and grasping all relevant interaction between the inputs and the output. Here, to be more precise, in the experiments we have done, we noticed that we didn't diminish a lot the accuracy of Cyrus compared to random forest, meaning that limiting, in our cases, limiting the depth of the tree is meaningless in terms of accuracy. So of course we lose a bit between Cyrus and random forest, but not so much, which seems to say that for this data set at least, maybe a right number of right order, of interactions would be of 2, and we tried to run the same experiment for a tree of depth 3, and it did not improve the accuracy performance. Yeah, so maybe I can leave the floor to Sébastien and Clément if you want to add some things.
Or Gérard, if you want to
Yes,
and present you, please, Gérard.
Maybe a short comment. So I'm Gérard, I'm professor at Sorbonne University, and I'm working with Erwan, Sébastien, and Clément. Yes, I think Erwan pointed a very interesting feature of Cyrus algorithm is that in the experiments, the decrease of accuracy of Cyrus is surprisingly small with respect to random forests, and especially when the algorithm outputs just 10 or 11 rules, and the performance stays really, really excellent. So I think that that's an interesting route to have a better understanding of what is sparsity, in the sense that maybe a way to think to the problem is to just saying that the function we are looking for can be approximated by a small number of rules, of very simple rules, elementary rules, and that the algorithm is able actually to find these rules and to compute these rules. So it's a different way of looking at sparsity, not in terms of number of important variables or influential variables, but in terms of influential rules. And that's maybe, Nicolas, what you had in mind, in fact, when you asked the question. And this is actually what the experiment suggests. And from this point of view, I totally agree with the answer of Erwan. Yeah, that was my answer, Bertrand.
Thank you very much. Excuse me. Maybe someone wants to go in the discussion? No? Sébastien, maybe? Claire?
Yes, actually, we were prepared for this question, and we discussed about it with Clément and Erwan. And actually, there are two things. Yeah, there is first, can we modify the random forest itself? And then, if we fix the random forest mechanism, can we modify Cyrus to detect higher level interactions? So Erwan and Gérard discussed the fact that we keep the current random forest implementation, and we have made several tests to change the depth used by Cyrus. But actually, we were discussing last month with Erwan and Clément if we could adapt the random forest design to focus on regions of interest. So for example, in the regions where the output will be larger than a threshold, which I think coincide with the concept of a critical situation that Nicolas had in mind. And so we are thinking about adapting the splitting criterion so that it focuses on these regions. And for example, by using ideas that are used in quantile forests, by using a pinball loss instead of the variance that is used in the current criterion. So this is also maybe a way of handling this type of situations, where in this case, maybe the random forest will highlight higher level interactions with the different splitting criterion.
Okay, thank you. So Nicolas, you have a last comment on this topic?
No.
Okay, you are plainly satisfied by all these answers, answers from specialists. Okay, so I think we can pass to the second topic. Well, I think it's very closely related to the first one, of course. This is the cooperation between machine learning systems and rule-based systems, which is, in fact, the Cirrus is one of these possible connection. But so maybe Jean-Michel, you have sent me an email about this kind of things. So I would like to listen you on this topic if you have something to say.
Yes, just a short mention. I am Jean-Michel Poggi, and I am now interested in random forest. And when I read some years ago the beta version of the paper, which is now published in Electronic Journal of Statistics, if I remember, the paper on Cirrus, it was something reminiscent from my old years, because when I work on my PhD, I use some kind of cooperation between Prolog, rule-based system, and numerical systems. So my question is about this connection, but as a system to make the cooperation between numerical world and the symbolic one, in a way also to complement the knowledge which are extracted from data, and Cirrus is a system which allows that. But my interest is that rule-based system, the interest is the possibility to incorporate and to encode business knowledge or expert rules. So my question is how to organize such a cooperation, not only from the methodological point of view, but of course, including this, but also from the practical viewpoint, how to put this in the information system, in the collaboration with the experts, to get knowledge, to put this on the system, and to try to improve the overall performance. So it's more a question than a comment, but it's my question.
It's a good question, of course, Jean-Michel. So maybe someone from the audience with an industrial point of view, with an experience of the subject of Jean-Michel, can come in the discussion. I don't know everybody in the audience, but do not hesitate to raise your hand. But if you are shy, no problem. I think about one colleague, my colleague Christophe, but Christophe, if you don't want to intervene, no problem. If you want, do not hesitate. I know that you have some experience about that. No?
But if I may...
yes, Christophe, come on.
Yes.
Yeah. Hello, I'm Christophe Labroche from Thales. So I'm not expert in random forest and so on, but we actually work on what some people work hybrid AI. So it's exactly a combination between machine learning or deep learning AI and symbolic AI, especially in the way Jean-Michel describes. So this is the point is to incorporate domain knowledge from experts into a systems. So one way to do it is to incorporate some properties like symmetry directly in the architecture of the neural network. So of course, it's quite different from rules at this point. And also we actually are working also in decision models, which are coming from economics. So it's a field which is quite close to game theory on this Shapley value that we heard this morning. On the some work we did is to transform this model on to achieve to incorporate them into a neural network architecture. And especially in these models we have a lot of formal properties we want to ensure, like monotonicity of inputs with respect to outputs and so on. And we want to have the neural network to satisfy all these properties. Usually people penalize the cost function to add this property, but in this case it's some kind of loose function. I mean, it's not a hard constraint; it becomes soft constraint, but it's not something we want in many domains. If you learn your model or your model violate these properties, it can be catastrophic for the end user. So we want for sure to have this. So there's some work we did in this area, especially. And I know there's some colleagues that are trying to, they are working on unsupervised learning and try to have for clustering, for instance, and they wish to have some let's say give a feedback on clusters they construct and have a feedback from users and from end users on from these feedbacks. Feedback can be, I don't want this node and this node to be in the same cluster, and from information like this try to modify the clustering methods. So I think the point here is also to have a discussion on a connection between end user and the AI, not having some kind of monodirectional box that you have an AI that produce a prediction or whatever it should produce that is displayed to the user on that's it, but you have a feedback. How the feedback of the user can be modified or incorporated inside the AI algorithms in order to better fit to the needs and so on of the user.
Okay, thank you. Thank you very much. I have seen one hand. Thank you very much, Yannick.
Thank you, Bertrand.
Please.
Thank you, Bertrand, for giving me the opportunity to talk. I just have an experience to share with you on how did we use random forest recently, coupled with more interpretable models. We will talk about this afternoon about additive models. And recently during the COVID crisis, what we experimented is to transfer information from GAM models to random forest, just using GAMs to fit some data transformations which are explainable, and then use this transform variable as inputs of random forest, which was used to adapt our models to the breaks, the changes due to the COVID crisis. And what I think was interesting with this idea is to exploit the good availability of GAMs to extrapolate out of data, which was the case during the COVID crisis. And at the same time use the nice availability of random forest to find some interactions between covariates and also the possibility to adapt with time to changes in data distributions. So I think it's something maybe also we can have in mind with random forest is what do we do when we extrapolate a little bit out of the limits of the data sets we use for the training.
Okay. Thank you for all these comments. From in Napoli, someone want to say something, or you all sleep after the fiesta of yesterday night? No. Okay. Okay. We have 15 minutes left. We can pass to the third topic, I think, because we have a lot of things to say. So the third one is on the need of clarification when we talk about explainability and interpretability. So what I wanted to show in this slide, excuse me, is Sébastien has talked about this topic, is a close connection we can see between what we call the computer experiments framework and the machine learning framework. So here I showed just two pictures which are we product in my company EDF some methodological picture to explain to the engineers different steps of methodology. So for the question of uncertainty quantification in computer experiments, we have provided the picture in the left, okay, which allow us to explain very clearly to engineers the different steps in an uncertainty quantification exercise. Okay, so what is important is to well specify the problem, to quantify all the sources of uncertainty, to know how to propagate this uncertainty, to know how to perform sensitivity analysis, which is very closely related to uncertainty propagation, to validate, to calibrate, etc., etc. And so now we all talk about the machine learning issues. It's not new, but it comes to us in very strong needs for industrial needs. And so we try to develop such clarification of the different steps which are involved when we want to develop and use a machine learning model. Okay. So I will not explain anymore because this is not the goal of the roundtable. But what I can underline on this slide is that in the global sensitivity analysis literature, as Sébastien explained this morning, is that many authors, many people have tried to clarify the main goals of sensitivity analysis, of global sensitivity analysis especially. And it has taken many years, maybe 30 years, to have for us a very now clear picture of what kind of questions the user have to ask before making a global sensitivity analysis. So for us, we can try to develop these different settings. So for example, do you just want to explore your model, understand the important interaction, understand the nonlinear behavior of the input on the output, etc. Do you want to just to make a factor prioritization exercise? It means that you just want to detect the non-influential inputs. Do you want to, no, this is the factor fixing, excuse me. The factor prioritization is to understand very finely the share of inputs in the uncertainty of the output? Or do you want to make something different, like a robustness analysis? It means that you want to understand the stability of your quantity of interest with respect to the assumptions, for example, the probabilistic models that you have put on your inputs. Okay, so for us, the global sensitivity analysis is very clear. Well, of course, we are specialists, but it's very clear. But what we can ask now some question is about the interpretability and explainability, because in the literature we can see that it's not clear at all. Maybe for some of you it is clear, and so what I can say now is to give the speak to people who want to discuss about this, what kind of settings we can put on the interpretability issues with respect maybe to the audience. Okay, so excuse me, I have to see if someone want to make a comment about this, to share his experience.
Yes, maybe Bertrand, one quick comment.
Yes, thank you.
Yeah, so maybe two quick comments to these very interesting questions. First, a comment regarding the vocabulary. I think that one of the key challenges in the field is that we lack a common language. This morning we are talking about interpretability, but to me, interpretability is not necessarily explainability. And actually, many colleagues regard interpretability as a sort of comprehensibility of a model or of model output. And we may also view explanations actually as something which is more encompassing, in the sense that interpretation, as we have seen this morning, is more concerned with comprehending what the rules of a specific system are. Whereas explanations may include, of course, interpretation of the system, but as well some justification of why the rules are and what they exactly do. So I think it's important to have a clear and sound definition of what we are talking about. And to me, explanation is something more large. And we are getting back to the discussion that we had 5 minutes ago regarding the importance of the audience. I think that the dialogue between the user and the algorithms is very important if we want to speak about explainability. So that was my first comment. And my second comment was regarding the connection between sensitivity analysis and variable selection. I think we have seen this morning that both fields are connected, but there is still one important gap, I think. The gap is that in sensitivity analysis, at least for what I know, the population, well, the quantities of interest are well defined in terms of, I mean, at the population level. They are defined in terms of conditional expectations. They are defined in terms of increase in variance, etc. That's the case for the Sobol indices, for the full Sobol indices, for the Shapley effect. So we know what we are after. And for that, we have algorithms, we have heuristics, which estimate things which are clearly defined. The situation, unfortunately, is a little bit different with the variable importance analysis, and typically with the MDA and the MDI that we have seen this morning. These quantities are based on heuristics, on algorithms, or on methods on top of algorithms, which are, of course, computationally efficient. They provide results, but we do not know exactly what these methods are doing. And I think that this is problematic, of course, because in some situations they may be interesting, but in other situations, well, the results may just be unclear. And from this point of view, the work of that Clément presented this morning, I think it's very important because it clearly shows that in some cases we should use this importance variable criterion, but in other situations, for example, when there is a lot of dependencies between the variables, etc., we all know this type of situation, then this criteria should be clearly avoided. So that was my second claim, having more math into a better understanding of this variable importance criteria.
Exactly, and it is. Thank you very much, Gerard. And it is a perfect link with my last topic, which is about the needs of clear definition, of clear positioning of the methods, of the different methods, of possible to get estimate with controlled uncertainties on the importance measures, etc., etc. Okay. So this last slide, and after we have again 5 minutes to discuss about, is just to show you that in the global sensitivity analysis literature, there has been very strong efforts to make a kind of a taxonomy of methods, but with clearly the hypotheses are clearly stated for each method. So you see that this is a picture from one of my publications, but it's not very important. It's just to underline that we have this kind of picture to put in front of our engineering studies to explain what the methods that the user can use. If you are a very costly computer code, so you have to take a method at the left of this field. And if it's not costly, you can relax the hypothesis and take more efficient methods. So there is, for me, there is a real need to have such picture in the interpretability literature. So Vincent, one of my colleagues, want to say something. So Vincent, okay, you have the floor.
Okay, thank you, Bertrand. So hello everyone, I'm Vincent Touvenot from Thales. So I'm a research engineer, and as said Bertrand, there is a need of clear definition for the interpretability method in machine learning. For example, if we are doing some local explanation of outputs of machine learning models, in this case, a popular approach is to use the Shapley values, in particular with the Python module named SHAP. However, in this context, the game behind this approach is not always well defined in the context of machine learning. So in SHAP, for instance, they compute the attribute importance with many approximations. So in fact, we do not know really what is computed. And finally, we have a black box model that we want to explain and interpret. And for that, we will use some approaches, sometimes without a well definition and without theoretical properties. So that raises some question. Moreover, the validation and the evaluation of the approaches, which is linked with that, raise some question too, and things like that. So I think for that, the work that Clément present this morning is very important, because it gives some first some theoretical properties and things like that. And okay, so that's
thank you. Yes, thank you. And there is another Vincent who is also French and who has raised his hand. Up. How to open the microphone of Vincent Chabridon?
I turn it off. Can you hear me?
Yes, thank you, Vincent Chabridon. You
Thanks.
are the second Vincent.
Yeah.
Vincent.
Yeah. So my well, it's not a question, it's more a comment, but it's more about the topic 3. So maybe you can come back to the 2 beautiful schemes. So it's more common. I think one major difference between the 2 paradigms is that in sensitivity analysis, so you manipulate the real basic variables, so the physical variables, and their distributions. So your data are like the primary information, but in machine learning, most of the time you have more complex mathematical quantities in input. So, for example, time series or even images or whatever. But let's stick to time series. And so you have to extract some features, and sometimes you extract many features for the same variable, because summarizing a complex time series is a complex task. So you can generate for one time series, for one variable, many features, like I don't know, 10 features, for example. And so then you have to deal with the expert engineers and to discuss with them which are the features that are more or less useful for them, because they can understand and manipulate them somehow. So you have like several variables for one variable, and these features can be highly correlated. They can be collinear, multicollinear. So, well, I don't know how the speakers of the today's speakers, what do they have in mind about this kind of problem? Well, I'm not really using random forest, so I'm not an expert, but I'm just wondering if
it's an important question. The highly multicollinear case, which are maybe omnipresent in real industrial problems. So maybe we can have answer from a theoretical point of view, and after from a practical point of view with Sébastien. And I think after we can stop the discussion because we are all hungry.
Sorry for that.
No comment from the Safran engineers? And Clément can say something also.
Clément, do you want to speak?
Go ahead, Sébastien.
Oh, okay. Thank you, Vincent, for the very tricky question. I hate you. Actually, I don't have the slightest idea about how we could adapt Cyrus to handle these cases, to be honest. So I don't know at all.
Well, it's a very difficult question, but
it's
an open question. It's fine if you want to finish on very open question.
Yeah, it's not a trick. It's just I'm really interested in.
Yeah. No, but for the variable importance point of view, I can answer. But building an interpretable model with such complex inputs, I really don't know how we could handle that. I don't have any idea. Maybe Erwan or Gérard. But...
And there are a lot of issues also in terms of variable importance when you have an high multicollinearity, because Shapley effects are not the panacea. I don't know how to translate panacea.
Yes, because everything is mixed, but yeah,
everything
we still have a long way to go in sensitivity analysis to propose even better indices to handle that. Yes.
Yes, it's a very long way.
You know that better than me.
Yes, it's a long way to go to the top, of course. Okay, so it's 12:35. Maybe someone wants to say something to conclude. I can conclude, of course. So thank you very much for the participation of all the audience and of all the speakers. Thank you, Jean-Michel, and thank you, everybody.
So see you at 2 p.m. for the pilot 2.
Okay.
Bye.
Okay. Forza Italia, of course.